For 8 episodes now, every example arrived with a label. You knew the right answer, and all the learning did was measure how far the prediction missed, then nudge it closer. Reinforcement learning keeps almost everything about that picture and changes exactly one thing: the signal. And that one change is the whole episode. Here is the change. You no longer get told the right action at each step. Instead, you act across a whole trajectory, a long chain of decisions, and only at the very end do you get a single number: the reward. Every bit of learning now has to be backed out of that one number, spread thin over many choices. Picture it, a run of actions, and at the finish line, one score for the entire attempt.
That sounds like a completely different subject. New machinery, new mathematics, the works.
It sounds that way, and it mostly is not. It is the same subject, with the training signal reshaped. By the end of the next few minutes, you will recognize reinforcement learning as an old friend wearing a new coat. Start with the thing that acts. We call it a policy. A policy is just a softmax over what to do next, the very same output head you have seen on every classifier in this series. Feed it the current state, and it hands back a probability for each action you could take. Up, down, left, right, each one gets a share of the belief. Now play a game with me. Suppose, just for a moment, that you knew the correct action at every step. How would you train this thing? You already know the answer. You would reach for cross-entropy, the same loss from the very first episode, whose gradient is simply the predicted probability minus the one hot label.
But that is exactly what we do not have. In reinforcement learning, you never know the correct action.
Precisely, and that is the entire difficulty. The answer from an algorithm called Reinforce is almost cheeky. Use the action you actually took as if it were the correct label, then weight its gradient by the return you earned. Trajectories that paid off pull the policy hard toward the actions they took, the ones that did nothing barely tug at all. It is cross-entropy, reweighted by reward. You do not have to take my word for it. Here is the gradient itself, lifted straight from the from-scratch code that trains the agent. 3 lines carry the whole idea. Watch how little happens. Start with the policy's probabilities over the actions. Then subtract 1 from the probability of the action you actually took. That single line, the predicted probability minus a one hot label, is exactly the classification gradient. Nothing about it knows it is doing reinforcement learning. It is the same arithmetic you would run to tell a cat from a dog. Then one more line. Multiply by the weights, and the weights carry the return. That multiplication is the entire difference between supervised learning and reinforcement learning. The gradient keeps its shape. The reward simply scales it, strongly for the trajectories that paid off, and hardly at all for the ones that did not. The body is still a small feed-forward network. The head is still a softmax. Only the training signal changed shape from a per-example target into one scalar smeared across a whole sequence.
Wait, if the reward only shows up at the goal, how does a move back at the start ever get credit for it?
That is the hard part, and it has a name: credit assignment. The reward arrives at the end, but the trajectory is a chain of decisions, and something has to decide which of them earned the score. Reinforce's answer is blunt. Scale every action in the trajectory by the total return. That estimate is unbiased. And it is very noisy. Most of the machinery of modern reinforcement learning, the baselines, the value functions, the advantage estimates, exists for one purpose: to cut that noise without bending the estimate. The honest one-line summary of the whole field is this: the gradient is easy. The variance is the problem. And still it works. Point it at a 5x5 grid world with a single reward waiting at the goal. Early on, the agent just wanders, bumping around with no idea where it is going. By the end, it walks a near-optimal path, the return climbing close to the best you could do. It learned to navigate from nothing but a number handed over at the end of each attempt. That is a small thing, and it is worth pausing on. So where does all of this top out? The theoretical optimum has a name, AIXI. Bolt together Solomonoff induction, the optimal predictor, with Bayesian decision theory and pure reward maximization, and you get the agent that does the best possible thing in any computable world. It is also completely incomputable, which is the very lesson that has run under every episode. The ideal is out of reach. Every practical method is an approximation, and the assumptions baked into that approximation, the inductive biases, are what decide what it actually learns.
So even here at the very end, it is the same lens.
The same lens exactly. There are 3 places to encode what you assume about a problem: the architecture, which functions are even reachable; the output head, what the numbers are allowed to mean; and the training signal, what counts as success. Supervised learning fixes that third one as a per example label. Reinforcement learning keeps the first 2 and rewrites the third into a reward over trajectories. The bias lens never changes, only where you spend the bet does. One last scorecard, the same 3 rows we have filled all series. The bias, the return tells you which of your own actions are worth imitating. The win, it learns from a single number per episode, from almost nothing. And the bill, noisy gradients and slow, uncertain credit assignment. Now step back and look at the whole series at once. A convolution bet that meaning is local. Recurrence bet that time is homogeneous. Attention bet that relevance can be computed from content. Every architecture we met was a wager about the shape of the world, paid back in sample efficiency when the bet was right, and paid for in confident failure when it was wrong. Every architecture is a bet. We read reinforcement learning here from the architecture side as one more place to spend that bet. What reinforcement learning assumes more broadly, about reward, about agency, about how an agent should explore, is a whole story of its own. That is its own series, coming later. Thanks for watching.